because last time I checked, it hadn't been moved yet. But the request went through on Friday, so we'll see. I'll write it down. Get all this set up before I forget anything. Great. Okay, so I guess good news for me. The labs have unofficially been moved. I'm just waiting for it to go through officially. They've been moved to Mondays. So LO2 is at 1 o'clock. LO1 is at 5 o'clock. I know that's late, but like I said, you're welcome to come to any of the labs, right? Or none of the labs. And I do have labs at 4 on Mondays and Wednesdays as well, okay? So once those all get put through officially, right, I'll let you guys know all the lab times and give you a little lab outline sheet, okay? Yeah, I know, but then Mondays work better. I figured since we have class on Mondays, I kind of stuck to Mondays. Yeah.
So today we have a lab?
There will be labs, so I'll host labs today, but because it's kind of this weird unofficial week, I'll also host the Friday labs. So if you'd rather go to the Friday labs this week, you're welcome to. I'll be there. And then next week, we'll just have the labs on the Mondays. Okay? So like I said, kind of still unofficial. When it's official, set in stone, I'll give you guys the outlines, and then you'll know exactly when and where the labs are. Okay, so let's just jot that down. So labs have, I'll say unofficially moved. So LO1 is at 5 o'clock on Mondays. LO2 is at 1 o'clock on Mondays. I also have labs Monday, Wednesday at 4 o'clock that you're welcome to come to. And then for this week, I'll also host the Friday morning labs. Okay, so for this week, I will also host the Friday morning labs. No, you can use the school computers. If you want to use your own computer, then I can help you download it. It doesn't take too long, so yeah. If you want to make sure that you get it all kind of set up, then maybe bring your laptop and we can get it set up. Yeah. Yeah. So turns out I need help kind of merging all my lab sections. I want to have just one to manage. I've done it before, and for some reason I cannot figure out how to do it again. So anyways, I'm going to do that. Steve has to help me. So anyways, once I get that done, I'll post the lab manual. It's still in kind of its draft phases, so there's little typos and stuff, but overall the material is all there. And so it'll have the instructions for how to install R in RStudio, and also there's videos for all the labs, right? So they are long. I have every intention of making shorter ones, but making videos takes a long time. So just kind of make do with those longer labs. So there's I think five lab videos on YouTube already. So you can kind of work through the labs on your own, because that's basically what I would do in the lab. Just kind of read you the instructions and then you work through it on your own. Okay. So you have, or you will have all the tools to work through the labs on your own. And then the lab time, how I would prefer that you use the lab time is just to ask me questions. Hey, I tried this, it didn't work. Why didn't it work? Why isn't it working? It's going to be a lot of, why isn't it working? Right? But that's okay. Right? And so this week, you know, we're just getting started. And like I said, I'm not expecting you to know anything about anything for this, I don't know, first half of the term even. Okay? So just ask questions, kind of do your best. That's all you can do. Okay? So finish my, so for this week, I'll also host the Friday morning labs, just because. Okay? But then for next week, we'll have officially moved. Okay? Let's steal, only because I know this one's available, C286. C286. Good question. I think I bounce around a little bit. Let me see here. Mondays, I'm in C184. And on Wednesdays, C286 again. Not too bad. I can't remember where the Friday labs were scheduled, but those should be on your schedule still. Okay. I'll figure that out for Wednesday. Give you guys a heads up. Okay. So come to any of the labs. I would say come to the first week of labs. And then if you feel like this is something that you can handle on your own, kind of manage your own time, that's fine, that's great, right? Just kind of use me if you have questions. Okay. So yeah, any other questions about that? Or we kind of move on. Great. Okay. So a little bit of review. We covered a lot of ground, right? A lot of terminology, a lot of kind of things we need to know, right? So we talked about data collection. Data collection. Need to have a random sample, right? To make sure that our sample is representative of our population. So we need to have a random sample to ensure our sample is representative of our population. We also talked about the importance of reporting the response rate, right? If we're reporting on survey data, which happens quite a bit, right? We have to report the response rate. So when reporting on survey data, we must report the response rate. Low response rates yield less reliable results. Low response rates yield less reliable results. then we talked about bias in our sampling. So we talked about bias in its many forms, right? Non-response or voluntary samples or all these things that kind of give you a biased sample. So any sort of bias is when you're systematically favoring one outcome. Right? So it's when we're systematically favoring a specific outcome. Right. And we said this is all bad sampling. So we just kind of plowed through, how do we collect our data? Right. And then we talked about, we have two methods, right? In general, we can do an observational study, right? Where we just go out and we ask people how tall they are or what brand of milk they buy or whatever, right? So we're observing information, right? Or the other path is an experiment, which doesn't really apply, I don't know, for you guys if you're not in sciences, maybe you guys, right, so experiments are kind of their own beast. And so we talked about two ways of collecting data. Oops, keeps erasing my last word. One is through an observational study. And two is through an experiment. One thing that we did say about experiments was that an experiment is the only way to establish a causal relationship, right? So a change in this causes a change in this. An experiment is the only way that we can establish that kind of relationship, right? Whereas in an observational study, right, you can say that this changes with this, right? So there is a relationship here, right? But we can't say that this causes a change in this. And so we emphasize that experiments, oops, start that over. Experiments are the only way to establish a causal relationship. Causal relationship between two variables. Right? We'll be talking about the relationship between variables. So between two variables. And then for just a minute, we had a look at, okay, so how are we going to visualize these things? We'll start by visualizing a numerical variable, right? So to visualize a numerical variable, we use histograms. We use histograms. So that's kind of where we'll pick up today. Let's see if I can steal those slides again from here. Oops, doesn't matter. We had to look at this. Yes. So I'm just going to steal these. Now you don't have to copy these out or anything, well, unless you want to. Don't really see the point. Try to get these side by side here. So here, right, we have two histograms. We talked about these last day, right? So we said, okay, so we've got numerical data, right? And the whole point of visualizing it is to see the distribution of the data, right? And so let's just make a note of that. We visualize data to, I'll say, look at the distribution. So here, it doesn't matter what x is. We know we have very few x's between 10 and 15, right? Because here we're just kind of lining them up, right? So if you're in the 10 to 15 category, you go in this lineup, right? These are called bins, right? So you go in this bin. Kind of fun if you're thinking of you've got all these bins, right? And everyone's just kind of piling up, right? As you have more and more in each bin, right? The bar gets higher and higher. And then we reach a peak between in the 25 to 30 bin, right? That's the most common bin. And then we kind of decline again. Right? And so again, here we've got the same type of shape. Right? And so what if I called you on the phone like this? Oh, they did a study. I guess the banana is still the fruit of choice for pretending to be a phone. They gave people a choice of fruits. It's like, okay, pretend you have a phone. People grab a banana, obviously, but fun. It's been confirmed by studies. So you're on the phone, right? And you're looking at this and you're saying, oh man, I have this beautiful histogram here. Oh, what does it look like? Well, so now you have to describe this histogram. Right? There's going to be three things that we have to talk about always to describe a distribution fully. Right? We have to talk about the shape. Right? We have to describe this, and we talked about it just briefly last day. Right? This shape is so common that we call it the normal distribution. Okay? A lot of things just naturally follow a normal distribution. Okay? So the shape is the first thing you're going to tell me. Okay? Second thing you're going to tell me is, well, where's it centered? Right? What's a common value for these guys? Oh, and you just kind of quickly eyeball it, right? There's no math involved here. We'll get to the math later, right? But as far as just describing it, so you're on the phone, so I can't see it, right? You have to explain to me what it looks like. And so, I don't know, somewhere between 25 and 30, right? That's where the center is. That's where most of these values are. I'd say even between 20 and 30 is fine, right? Just rough idea. The idea is to pinpoint it. Is it between 100 and 150? Is it between 2000 and whatever, right? And so just to get an idea, between 20 and 30. Oh, okay. And so if we move over to this side, right, then we've got similar shape, right? And if you had to pick a center here, I would say around 20, 30, 40, right? So the center for these two is about the same, right? Roughly. Then we have to talk about the spread, right? So what's the, oh, I was just a second too late. Got to change the timer on this. Okay, so, right, so the shape is roughly the same for both of these. The center is roughly the same for both of these, right? But the spread, and I'm just talking about, right, from where to where does this data go from, right? What are some reasonable values that you can expect to see if you're collecting whatever this is? Right? I'd say between 10 and 40, right? And again, just rough approximations. Right? Are you going into the negatives? No. Right? Is it up to 100? No. Right? So you just kind of narrow it down, just rough, quick approximations. Right? So I just want you to eyeball it, essentially. Right? So eyeball the center, eyeball the spread. Right? Roughly from where to where does it go? And then, so looking at this one here, right? We've got the same shape, we've got the same center, but the spread here, roughly between -40 and 80. Because I don't like to do any more math than I have to, right? I'm just gonna pick whatever the values are on the scale, kind of go with that. Right? We could probably even push it out to -40 and 100 if we wanted to, right? So now we've got a way bigger spread here, right? So this one has a wider spread, right? So a wider range of values that we might expect to see, right? And so that's what we call just variability, right? There's a lot of variability in this data set, whereas this data here, nice and tight, right? Between 10 and 40. So that's where all our data points are kind of coming from. So there's less variability. So let's make some notes. Or any questions before we do? Make the notes first. Got it. Okay. So to describe a distribution, entirely, we must discuss three things. First one being the shape. And we'll talk about a couple of different shapes in a bit here. But as far as on a test goes, right, I'll give you a histogram, ask you to describe it. And so there, I just want you to choose between, is it normal or is it non-normal, right? So anything that kind of looks like this bell curve, right, we call it normal distribution. And one thing to keep in mind is that you're always pushing for a normal distribution. Because the normal distribution, well, one, it's the only thing we'll deal with in this term, right? But also it has just a box of tools available to us, right? So, but one of the assumptions is that we have a normal distribution, right? So we often assume we have a normal distribution, and then we say, with the exception of, you know, this extreme value or maybe a peak over here, right? So we push for a normal distribution, and then explain why maybe it's not exactly normal. Right? So as far as your choices go here, it's either normal versus just non-normal. Second thing we're going to talk about is the center. Okay. So just quick glance, right? Rough approximation. So if you imagine your data, right, kind of blanketed by this normal distribution, right? If you look at these, right, I'll try to do my best here. Where would the center be? The center would be somewhere around there. Right. So here's the center. So it's wherever you imagine the peak of your normal distribution to be. The problem with histograms is that we've just collected so many data points, right? It's only once we have the whole population that it'll be this nice smooth curve, right? But I just imagine kind of draping a blanket over it, smoothing it all out, and that's what your normal distribution looks like. Okay, so here, that would be your center. Okay. So you just kind of eyeball it. I'll say eyeball it in quotes. I don't know if it's a real thing, but it got pretty famous. So when I worked at the market research firm, I was kind of the lead statistician. So they would come to me with all kinds of weird problems. And at the end of the day, all I said was, they're like, oh, so how did you arrive at that? I was like, oh, you just eyeball it. So then I was just the eyeballing, I don't know, the resident eyeballer. But I mean, eyeballing it, it's a skill. I guess it's stats. Stats is all about eyeballing it. Is it big? Is it small? Where's the center? Right? Are there differences? Just eyeball it. Okay. So that's why I use the term eyeball it. I don't know if it's a thing. Then we need the spread. Again, just a rough approximation, right? It's just to give an idea of the realm of values that we're expecting to see. Right? So again, just a rough approximation. Eyeball it again. So if you think about your endpoints A and B, right? So roughly between A and B. So you would say something like from A to B, roughly. So here, let's call this histogram number 1 and number 2. So describe histogram number 1. Shape, center, and spread. for number one. Now I've drawn on it, right? But number one, we said normal distribution. Okay. Like I said, if it looks anything like a normal distribution, you're gonna say it's normal. So normal. The center we said was around 25-ish. You can give a range if you want. Somewhere between 20 and 30. Right. And the spread, we're expecting to see things between 10 and 40. Right. So if I said, okay, so you see a value of 37, right? Would you say that's weird, or no, that's fine, right? It's on the upper end, right? But it's still within the realm of what you are expecting to see, right? What if you see a data point that's -2, right? That's kind of out beyond where we're expecting to see it, right? So a lot of stats is saying, well, -2 is this far away, right, from where we're expecting to see it, and so something's going on there, right? So this idea of having an acceptable range, right, and being able to detect things that are outside of that range is a lot of what we'll be doing for the rest of the term. Okay? So the spread somewhere between 10 and 40. Right. What if we just do the same thing quickly for histogram number 2? We already decided the shape was the same and the center was approximately the same, right? Shape was normal. Center was around 25. The only thing that was different was the spread. Here we have a spread from -40 to, I'll say 80. I know you'll be tempted to do a little bit of quick math, right? Each bin has a width of 20, so another bin on top of 80 makes 100, right? But I just want you to look at them and quickly say between here and here. So between -40 and 80, I'll say, or 100. Yeah. So now all of a sudden, if I gave you a data point of -2 for this data set, that wouldn't be that strange at all, right? It's hanging out with the rest of the crowd, right? And so the variability in a data set is going to play a huge role. Okay. So since histogram number 2 has a wider spread, right, it has more variability. Since histogram number 2 has a wider spread, it has more variability than histogram number 1. So that's just quickly describing a distribution. So looking at a histogram, right, and just quickly coming to terms with what's in there, right? What does our data look like? Well, it's approximately normal, centered on this, with range of this, right? Now you have a good idea of what your data looks like. Okay. Of course, right, we're not just going to be eyeballing things, right? We're going to do calculations, right? So there's numerical measures of center and spread, right? And so now let's look at some numerical measures of center and spread. So just how do we calculate values to attach to these? So depending on if we have a normal distribution, right, which means we have to have seen a histogram of it, right, or some sort of visualization of our variable, right? If we have a normal distribution, then we calculate the mean and the standard deviation as our center and our spread. Okay? They're the most powerful, right? But we have to have a normal distribution to use them. Right? We can always calculate them, but we should only use them if we have a normal distribution. Okay? Whereas if we have a non-normal distribution, then we should be using what's called the median and the interquartile range. Right? So what we're about to do is just kind of work through these calculations, right? How do we find all these things? Right? But that's where we're headed, right? So we have center and spread for a normal distribution and center and spread for a non-normal distribution. So depending on if we have a normal or non-normal distribution, depending on if we have a normal or a non-normal distribution, our numerical measures of center and spread will be, so if we have a normal distribution, the center that we'll calculate is the mean, which we already know is the average, right? But I'll make a note here. And for the spread, we'll use the standard deviation. We've talked about the link between the standard deviation and the variance, right? The variance is the standard deviation squared, and the standard deviation is the square root of the variance, right? But for us, just to simplify things a little bit, I'll just use the standard deviation, right? So it's your job to know the link between the variance and the standard deviation and not be thrown off if you're given the variance, right? You can just take the square root of it, and then you have the standard deviation, right? But we'll just pick one and stick with it. Okay? So if you have a normal distribution, then for the center, you're going to use the mean, and for the spread, you're going to use the standard deviation. Right? If you have a non-normal distribution, for your center, you're going to use what's called the median. And for the spread, we're going to use the interquartile range, which is abbreviated IQR. So the interquartile range, or the IQR. So the mean and the standard deviation they're not resistant to outliers, meaning that if you have an outlier, so an extreme value, the mean and the standard deviation are going to be impacted by that. Right? Whereas the median and the interquartile range, they kind of stay where they are. Doesn't matter if you add a huge value, right? It just counts as another value. And so we can use the median and the interquartile range for any distribution. Okay. But the mean and the standard deviation are more powerful, right, for our calculations and things like that. But we have to have a normal distribution, right? And so we can use the median and interquartile range and interquartile range, IQR, for any distribution. But the mean and standard deviation are more powerful if we have a normal distribution. Are more powerful. Oops. If we have a normal distribution. So I'm going to show you how to calculate all these things just by example. Okay. And so, I don't know, I've got this kind of boring one that I'll have to change, but just as an example, the distance flown in a day by 9 parrots is recorded below in kilometers. Should have thought of a funner example. Oh well. The distance flown in a day by 9 parrots is recorded below. In kilometers. So this example, we're going to calculate the mean, we're going to calculate the standard deviation, we're going to calculate the median and the interquartile range, and a little bit more. Okay. But we can use the same data set for all of these, right? Just to show. One side note is that I am really opposed to doing calculations by hand, but I have to teach the same thing that everyone else teaches. And so I would just say, no, your phone can do this. Why would we do it by hand? I have no idea. But anyways, here we go. We have to learn it. We have to do it. I guess it's just a fun exercise. So I'll try to alter these to make these a little bit more fun. 2.8 kilometers, 1.3 kilometers, 1 lazy parrot, half a kilometer, 4.7 kilometers, 3.5, 7.1 kilometers, 1.9 kilometers, 2.1, and sneak in my 3.4. So if we break this up into parts, right, part A would say, find the mean distance flown. Find the mean distance flown. So I think we're all capable of finding the average of these, right? We add them up, we divide by 9, just because there's 9 numbers, right? But this is also a good chance for us to introduce summation notation, because it is something that we will be using, and I'm not sure how familiar you guys are with summation notation, right? So the mean, the sample mean, right, is X bar, right? So imagine just in a spreadsheet, right, if we recorded each of these 9 numbers in a spreadsheet, at the top we would say, here's X, right, where X is the distance flown, and here are all the numbers, right? So we just use X in general. Okay. And so X bar is the sum of X over N. Where the sum of X, right, so read it as the sum of X is all the X's added together. Which is what you would do, right? If I just asked you, find the average of all these, right? You would take each of these, add them up, right? So that is the sum of X. And N is the sample size. Okay. This is the first time that we're seeing a little n, right? But it's going to come up a lot, right? So one thing to kind of lock in is that n is the sample size, right? Because we're going to come back and use that quite a bit. And so, right, the sum of X is all of these values added together. Let's see if I can, I'm going to cheat because I don't have them. You guys have them on your page, but my page is so small. So here, you can say something like X equals all these things, right? That's fine. If you want to link it back to X, if you don't, then that's okay too, right? And so if we just had to find the sum of X, the sum of X is 2.8 plus 1.3 plus 0.5 plus 4.7 plus 3.5 plus 7.1 plus 1.9, oops, plus 2.1 plus 3.4. Right now I'm wishing I hadn't changed the numbers, but here we go. Awesome. 27.3, anything else? No? No? Great. Oh, I guess there's only 2 or 1 decimal. Okay. If anyone else does it, just to confirm, then I don't have to do it, which is perfect. Okay. And so we added up all these numbers, right? So now the sum of x is going to be replaced by 27.3, just as you would do it if you were just doing it in your head, right? And n is 9, right? You can count up how many numbers you have, right? Or you can look at, okay, well, we're looking at 9 parrots, right? The distance flown in a day by 9 parrots, 9 carrots. That makes for a funnier example. But so our sample size is 9. Right? So now if we have to find x bar, right, which is our mean or our average, it's the sum of x over n. Now we can replace the sum of x with 27.3, and we can replace n with 9. Bless you. So I get 3.03 repeating. One thing I want you to get in the habit of doing, and it's just kind of me being picky, is I want you to, whenever possible, try to stack these equal signs, right? So I don't want you working across the page unless, you know, space issues. Yeah. How many decimals do you usually want us to go back? For here, it depends on the question. But for now, I want you to keep as many decimals as you can throughout your calculations, and then round to at least 2 decimal places. Okay. So round your answers to at least 2 decimal places. For now. Good question, because it will be question dependent. Okay. Later, it will depend on, oops. I love merging words, I guess. It will depend on the question. Okay. But for now, go for at least 2 decimal places. I'll try to tell you how many to use, right? But sometimes just go with at least 2. Good. So, oh, stuck. So there's the mean, right? We all kind of knew how to get there. Feels pretty good, right? What if, well, I guess we should state our answer as an answer. Question was, find the mean distance flown. The mean distance flown is 3.03 kilometers per day. The mean distance flown is 3.03. 3 repeating, I can just drop kilometers per day. One thing about stats is half of the game is actually answering the question, right? So if you're here because you love math, then I'm sorry, it's going to be a little bit more than math, right? If you're here and you are worried about the math, don't worry, it's only going to be half of it, right? And so a lot of it is just going to be the interpretation of these numbers and what do these things mean, right? Not necessarily how do we get there, right? In the real world, all these values we would just calculate using software or in our case in the lab, right? And so all these numbers we can get easily, right? And so our job is more the interpretation of these numbers, right? And even something as simple as stating our answer. Sometimes I'll get lazy and I'll forget to do it, but try to state the answer as an answer. Right? So the mean distance flown is 3.03 kilometers per day. Okay. Any questions about that one? Okay. What if we had to find, you guessed it, the standard deviation? Find the standard deviation of the distance flown. I'll just kind of repaste my numbers here so we have them on the screen. But the first thing that we need is, how do we calculate the standard deviation? Okay. So the standard deviation, the sample standard deviation, remember we denote by lowercase s. And there's a couple of different formulas, but I'll give you this one on the formula sheet because I think it's the simplest. So S is the square root of the sum of the x's squared minus n times x bar squared all over n minus 1. Yikes. So you can see why we had to kind of tackle that summation notation. Fun to say, fun to do, right? Because we need it here in kind of a bigger way, right? But remembering that the sum of x was just each of our x's added up, right? If you had to guess what the sum of x squared might be, right, you would probably make a new column, right, of each of these x's squared and add them up, right? Because the sum of the x's squared is not the same as the sum of the x's squared. Okay. So one thing to remember, is that the sum of the x's squared is not the same as the sum of the x's squared. So that's going to be important. So you can't just take the sum of your x's and square them. That's going to give you a whole wacky number, right? And so to find the sum of the x's squared, we need to create a new column with each x value squared, and then we can add all those up. We need to create a new column with each of the x's squared and then add them up. And then we can look at the rest of the values here, right? That's going to be the most of the work is here, right? Taking each of your x's, squaring them, adding them up, right? But then once you have that number, right, you can just plug that in here. Your n is still your sample size, And your x bar, that's the mean that we just found, the 3.03. We square that. And then we divide it by the sample size minus 1. And then we take the square root. So it's a lot of steps, right? But if you break it down, then really the only one that requires a little bit of work is this guy right here. So I'll copy out those, or I'll sneak those numbers here again. And what I'm gonna do to make things a little bit easier is, instead of writing them across the page, I'm gonna write them down the page, because then I can go across and square them. And for me, it just makes sense to look at them that way. I have a hard time going up and down for some reason. So I don't know about you guys. So I will write these values in a column. Like this. So I'll put X up top. Right? X in this case is the distance flown in a day, right? But X in general can be any of whatever data you're talking about, right, is your X. So X we said was 2.8, 1.3, 0.5, 4.7, 3.5, 7.1, 1.9, 2.1, and 3.4. If I add these up, we already found that the sum of X was what, 27.3? So now we're going to do the same thing for our x's squared. All right, so we're going to do our x squared here. (2.8 squared), 7.84. And I want you to keep all your decimals here. Depending on what calculator you have, I've got this business one, but all calculators I've seen have some sort of store function, right? So if you end up calculating a lot of big values, right, or a lot of decimal places, then you can usually store these values on your calculator, right, and then recall them for later. So if you want help kind of figuring out your calculator, we can do that after class or some other day. So 7.84, 1.3 squared, 0.5 squared is 0.25, 4.7 squared is 22.09, 3.5 squared is 12.25, 7.1 squared, 50.41, 1.9 squared, 3.61, 2.1 squared, 4.41, and 3.4 squared. And most calculators have a square button, so you can just use that. So not losing any decimal places here. If we add these all up, that's going to be the sum of the x's squared. And so here, the sum of the x's squared is, here we go, 1 plus 3. You guys will have to check my numbers because I tried to do 220 instead of 22.09. I'm getting 114.11, 112. 114.11. Probably missing oh, there you go. There you have it. So tedious, right? But once you know what you have to do, it's not hard, right? It is work to find all these squared values, right? And adding them all up. But once you have those, it's really not that hard, right? And so now we have the sum of our x's. We have the sum of our x's squared from before. Right? Oops. From earlier. Oops. X bar was 3.03. One kind of in and out is if I'm using values that I found in other parts, I can use the rounded versions, right? Whatever I rounded to in the previous part, I can use. Okay. And n is still 9. So now we can calculate the standard deviation. The standard deviation is the square root of the sum of the x's squared minus n times x bar squared over n minus 1. So now that we have all these components, we can just plug them in, right? And then be careful when we're calculating. So we save the square root for the very end, and we can replace the sum of the x's squared with 114.11. Minus n is 9. So 9 times x bar is 3.03. And that little guy is going to get squared, right? Just the 3.03 though. Over 9 minus 1. Okay. So I'm going to simplify the 3.03 squared times 9 first, right? And so I'm just going to get that to one number, and then it's easier to deal with. So 3.03 squared. I'll show all my steps here. So all under the square root still, 114.11. I'll drop the brackets because they're just around one number, so I don't really need them anymore, right? I like to have the brackets around the sum of the x's squared just to show that, hey, here goes a number, right, later on. But it's actually not necessary. Minus 9 times 9.1809 over 9 minus 1. I'll just simplify to 8. So 9.1809 times 9. 114.11 minus 82.6281 over 8, all under the square root. So we have 114.11 minus that previous answer. I get 31.4819 over 8, all square rooted. Probably the most common mistake I see when people are calculating their standard deviation is you've kept to the square root, but then somewhere along the way, you lose it. And it gives you a really, really high standard deviation. Right? So just be careful to keep your square root. So 31.4819 divided by 8. We need the square root of 3.935235. So square root that little guy, we get 1.983743305. Therefore, are you guys okay with if I use the therefore notation? Just 3 dots? Cool. So therefore, the standard deviation is 1.98, right to 2 decimal places, kilometers per day. Just with this little bit of time left. So there's the standard deviation. So I'll expect you to be able to know how to calculate the standard deviation, especially in the beginning here. And then later on, I'll just give it to you, right? I'm not expecting you to go through and do it, but it is something that you have to know how to do. Okay? So one thing that I'll just sneak in here, because I'm not really sure where they want us to put it, that we have to talk about is stem and leaf plots. Stem and leaf plots I usually ignore because they're a poor man's histogram. And like I said, our phones can generate histograms. You could just Google histogram generator, plug in your numbers, and it would just give it to you. So I'm not really sure why we need it, but a stem and leaf plot, stem and leaf plots are just a quick way to visualize a small set of numerical data. I call it a poor man's histogram. So remember our data here, I'll just paste it in, that we've been using. Okay. A stem and leaf plot is going to take a core chunk of the number, right? So the whole value in this case, right? Or tens if you're, tens, 20s, 30s, depending on your data, right? And so here, we're going to use the whole number as our stem, and then the decimal value as our leaf. Okay. The idea is that we sort this data from smallest to largest, and then we put our stems down, and then we tack on our leaves, and it generates this histogram looking thing. Okay. So stem and leaf plots, step 1, sort your data from smallest to largest. I guess you could do largest to smallest if you wanted to. Didn't really need to specify. I'll do smallest to largest. Okay. So in our case, we'll have 0.5, and I just like to do a little kind of tick mark after I've used it, or kind of cross it off or whatever. And then I've got, I think, 1.3, correct me if I'm wrong, 1.9, 2.1, 2.8, 3.4, 3.5, 4.7, and 7.1. Just double check, so count that you have 9 still, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Phew. Okay. to pick a stem, we will use the whole numbers. Write stems vertically. So our biggest stem here is going to be 7, right? So we go from a stem of 0 up to a stem of 7, right? And so we go from 7, 6, 5, 4, 3, 2, 1, 0. These are our stems. I separate them with a bar. Technically don't have to, but I think it makes it easier. And now, right, we can read from the top, right, 7. There's only 7.1. So you put a 1 as the leaf. Right. Yeah. Same thing for 4.7, right, moving down the list. So 4.7, we put a 7 after the 4. Okay. For the 3, right, for the 3 stem, we've got 3.4 and 3.5. Right. So after the 3, we start with 4 and 5. For 2, again, we've got 2 for the stem of 2, so 1 and 8. One thing to keep in mind is that each of these leaves have to take up the same amount of space, right? Because the idea is we're building up the bars in a histogram essentially, right? So one value takes up a certain amount of space, a second value adds on the same amount of space, right? And then we have 1.3 and 1.9, and then 0.5. Yeah. This isn't a really beautiful one, right? But if you tilt your head, I kinked my neck this week, so I don't know. But if you tilt your head, it kind of looks like a histogram. Imagine if you had more numbers on the 2, for example, then you would really have this kind of normal distribution. Right? So it's just a cheap, quick way to visualize numerical data. See you guys either later today or on Wednesday.